All right, we're at time. Sean, should we get started? Oh, there you go. I was gonna say I don't see Brendan on the call yet. All right, let's get started. We have a full agenda today, so we can utilize every single minute of this call. Um, all right, welcome everybody. This is KEYTRANS interim. We have decided to not do an IETF 121 session this time, just because some of the key participants are unavailable. So we're going to utilize this interim to go over all the progress we have made, and then all our authors have a presentation to share as well today. Myself, Prachi, and with me, Siobhan, chairs. Please note the note well. By participating in this call, you agree to follow all the processes, policies, and code of conduct set by IETF. As Siobhan mentioned earlier, if you want to come off mute or video, only do that when you have entered the queue and it's your turn to speak. Use of headset is strongly recommended. We have a pretty full agenda today. Brendan, Felix, Thibault all have updates to share with you all. So I think with that, we should just get started. We are still looking for a volunteer for note-taking. Is there anybody who would like to help? All right, no worries.
Hey, Thibault.
Yes, happy to not take, except when I do my presentation. So I will need someone else toward the end, but happy to do.
Okay.
Thanks.
Thank you.
I can take over while Thibault's speaking.
Perfect. All right. I think with that, first up we have Brendan. Brendan, are you ready?
Hi, yeah, I am.
All right. I can go ahead and share your I'm trying to figure out which presentation is yours, Brendan. There are a few here in the queue.
Oh, Josh McMillian?
Oh, there you go. Perfect.
All right. Cool. And can I drive as well?
Let's see. I don't think so, unless you want to share your screen.
I think there's a way to transfer control. Let's see. I think you might have to do that, Prachi. I think because you're sharing screen. So if you hover over Brendan's, over Brendan in the participant list, I think it should say transfer control.
Oh, okay. Let's see. Brendan. There you go. Okay, you should have the control now.
Okay, cool. So yeah, I am here to present the protocol document that I've been working on with Felix Linker. 1 second. Okay. So this is a slide that we have seen a couple of times before, but this is the basic kind of architecture that we're going for. We've got a user who is talking to a transparency log. I'm sorry, 1 second. But the user is talking to a transparency log. The transparency log is basically a key value database, and there are 3 types of queries that the user can issue. They can do search, update, or monitor queries. So a search query is basically looking for the value associated with some label. Update is changing the value of a label, and then monitor is an efficient way to check if for several labels, if anything unexpected has changed. And of course, the main thing to call out here is that we have now changed the terminology from keys to labels. So before, this thing that we were looking up in the transparency log was called a key, sort of to map to the key value database abstraction that we were going with. But that ended up being very confusing because we were calling the things that we were using to do the lookup keys, but also we were looking up keys in the transparency log. We were looking up public keys. And so we were like mapping keys to keys, and the terminology was too consistently confusing. So now we use labels. Labels are attached to public keys or other data, and yeah, and so that's how we call it now. In terms of how we actually build this system, the first thing that we talk about in the protocol document is what's called a log tree. And a log tree is a hash tree which stores information in chronological order. And the specific way that we build it is with a left balanced binary tree. And so the defining property of a left balanced binary tree is that every subtree is the largest possible, or every left subtree is the largest possible balanced binary tree that can be made with the data that you have. So on the left side, we have a picture of a tree like this that has 5 leaves. And so then the left subtree of the root node is the first 4, because the first 4 is the biggest balanced tree that I can make with the data that I have. And then that last 5th node is just stuck on as the root's right child. So log trees are nice because it's very easy to append new data. And it's also very easy to provide consistency proofs. And so a consistency proof is just showing that some new version of the log tree is the same as an old version of a log tree, just with new stuff added. So we're proving that nothing was removed in this new version. So that's log trees. The next kind of tree that we have is what are called prefix trees. And prefix trees are used more so for committing to a set of key value pairs. So the construction that we use for this is what's called a trie. A trie is basically a data structure that commits to some set of strings. And the defining property of a trie is that every node in the trie represents some prefix, and all strings stored below that node have that prefix in common. And then you kind of recurse down from there. So each node's left child contains all of the strings that share that prefix plus a 0 bit. And then all of that node's right children contain all of the strings that share the same prefix as it plus a 1 bit. So if you look at like the root node, the root node's left child contains all of the strings that start with 0. The root node's right child contains all the strings that start with 1. If you look at the diagram that we have on the left here, you can see that all of the keys are stored basically in like alphabetical order or like lexicographic order. And so when we insert new things into the tree, they can end up actually being stored anywhere. So on the right side, we insert a new value, insert a new key, which maps to the value f, and that's just stuck in the middle of the tree. But yeah, and then prefix trees are nice. Kind of how log trees have consistency proofs that they're useful for. Prefix trees provide search proofs. So if you already have the root node or the root hash of a prefix tree, then I can give you, some leaf node in here that says, oh, this key maps to this value, like this string of 0s and 1s maps to the value f. I can give you that leaf node, and then I can give you the copath of that leaf node, and you can hash those two things together. And you can check that they equal the root hash when they're all hashed together. And of course, that's nice because it proves that you got the same value as anyone else would if they issued the same query, if they also searched for the same key as you. So yeah, those are prefix trees. And then in the document, we combine them into what's called a combined tree. So in a combined tree, there's a prefix tree. The prefix tree contains every label to value mapping that is stored in the transparency log. And then we have a log tree, which contains the history of every version of the prefix tree. So if we're looking at this log tree, the prefix tree that's on the far left, that's going to be the first one, has basically just the first mapping that we ever inserted. Which is, the label A, which is maybe like a username or something, maps to the value B, which is going to be like a public key or something. And then as you go from left to right, you're building up more and more data in the prefix tree until you get to the end on the far right, which contains all of the current mappings stored in the log. So why is this different from last time? If you remember the construction that we presented at IETF 120, the way that construction worked is that it kind of like structurally only allowed changing one label's value at a time. And so now if you look back at how this works, in this first prefix tree, you don't have to just put one new mapping. You could put 1,000,000 in the very first one. And then in every new version of the prefix tree after that, you could put another 1,000,000. Like nothing stops you from doing that. And it would work just as well for the purpose of like doing the protocol. And so the, strictly speaking, building the tree in this way does make proofs larger, but it has the benefit of allowing what's called efficient preloading with fake or real data. So what happens a lot of times when people start a new log is they want to sort of preload it with all of their existing user base or maybe all of the data from a previous log. So they want all of that in there from epoch 0. And then they also want to add a bunch of fake padding data. And the purpose of that is to kind of hide how large their user base is. That's sensitive information for a lot of companies. They don't want to like deploy KT and then have a way for people to very accurately measure how many real users they have. And so that's preloading. That was pretty important to actually get working in the protocol. That requires this kind of ability to do batch changes, at least in epoch 0. And we considered for a while, like, is there some way that I can only allow this in epoch 0 and like not in the other changes to the prefix tree? But that was kind of weird and awkward. And also we realized that allowing batched changes in every epoch is actually a lot better for constrained use cases. So one example of this is if you are using the transparency log with post-quantum secure signatures, a lot of PQ secure signature schemes are more expensive to use. They can also have a pretty limited lifetime in terms of the number of signatures that you can issue from a public key if you're doing something hash-based. And so if you can batch changes, that can significantly reduce the number of signatures you have to make, and that can be very helpful for the log. Also, if you do particularly large batches, you can end up making the total size of the proof actually smaller, because you are basically just making less changes to the log tree, and then whenever you do a lookup in the log tree, that sort of copath you have to provide is a lot smaller because there's fewer things that have happened. So yeah, that basically motivates the changes that we've made since IETF 120. But if we look at this tree, this new version of the tree, let's talk about how do we actually search it. And this is the simple version first. So we have this combined tree. The way we look up in it is we find the most recent prefix tree root. Of course, that's going to be the one that's always on the far right of the log tree. And then we take that prefix tree root and we look up the label that we want in that prefix tree. And looking at that label takes us straight to the value we want. We look up, label C that maps to value D. And then we give that value back to the application and we're done and we can move on with our life. That is very tempting. It's very simple. The only real issue with it is that it relies on having a third-party auditor. Essentially, you need someone to go through every different version of the prefix tree and check that each version is constructed correctly. And then you also have to trust that person not to collude with a log operator to potentially like allow some change to the prefix tree that they shouldn't allow, to be able to give some malicious value associated with the label. So that's kind of the concern there, is that the security you get there really relies on the assumption of these two parties not colluding. And so we also discuss in the draft a different way to search the tree, which is more secure in that you're only relying on the structure of the tree to make sure that the responses to your queries are correct. And so that's nice because you're not relying on collusion. Like, you don't even need a third party. You are just relying on the structure of the tree. But as a consequence, it's less simple. So to kind of build up to this, the first kind of tool that you need is what's called a binary ladder. And at like a very concrete level, a binary ladder is just a series of lookups in a single version of the prefix tree. And so the reason we need to do that is because when we create new versions of a label, every time we create a new version, we insert a completely new entry into the prefix tree, which is unrelated to any of the previous entries for any of the previous versions for that same label. And the reason we do that is because it improves efficiency a lot. Not efficiency, it improves privacy a lot. But as a consequence, we need some way to find what the most recent version for a label is. And one kind of tempting way to do this is to just look in the prefix tree and see like, oh, you know, version 1,000,000 exists. And then I can see, oh, version 1,000,001 doesn't exist. And then maybe I can try to conclude that, you know, version 1,000,000 is the most recent. But what that kind of misses is you don't know that versions, you know, 1 through 999,000 all exist. And going through and checking that 999,000 versions exist in this prefix tree is not efficient. So what we do instead is we look up a series of versions in the prefix tree that correspond to greater and greater powers of 2. We look up versions that are greater and greater powers of 2. So what we do first is we ask, you know, does version 1 of this label exist? And we see, yes, it does. Then we ask, does version 2 exist? Yes, it does. Okay, does version 4 exist? Does version 8 exist? And we keep doing that until we get to the first version where we see that this version doesn't exist. And then what that tells us is that the most recent version is somewhere between these two. It tells us in this case that it's between 4 and 8. And so then between 4 and 8, we do a binary search to get to whatever the exact most recent version is. So halfway between 4 and 6 is, halfway between 4 and 8 is 6. So we asked, does 6 exist? Yes, it does. And then we asked, does version 7 exist? No, it doesn't. And the conclusion there is that 6 has to be the most recent version. And on top of that, we get this nice guarantee that anyone else who goes in and does the same process is also going to come to the conclusion that 6 has to be the most recent version that's available here in this particular version of the prefix tree. Okay, and so then tool number 2 that we need is binary searching in the log tree. So what this is, again, at a very concrete level, is just checking several different versions of the prefix tree to see that they're consistent. And the reason you have to do that is because if you think back to how we did the simple version of searching in the tree, we only looked at a single version of the prefix tree, and that can make it very easy to hide misbehavior because there could potentially be a new version of the prefix tree which is created, you know, every second, multiple times a second, and it's a pretty big burden to ask the person who owns a label to go in and check, you know, every single individual prefix tree and make sure that they're all formed correctly with respect to all of the labels that you care about. That's going to be too expensive to do, probably. So really what we want to do is we want to check, in essence, that before we accept a label, we want to make sure that it's where the label's owner would know to look for it, in essence. And so the way to kind of think about this is if the log tree tells us, or if the transparency log tells us that the first instance of some label or version or some version of a label exists at this point in the log, this is where it was first inserted, then there are 2 implications that come out of that. The first implication is that that same version of the label should not exist anywhere before there, and we can kind of look in there and check that. And then the second implication is that that same version of the label should have the same value at every log entry past that point where the first instance was. And when we do a binary search, we actually kind of enforce that. We look on both sides of where the first instance is, and we check that it didn't exist back here, and we check that it existed over here on the right side, and we make sure that everything on the right side is consistent with the first version. So to kind of work through an example of putting these 2 things together, whenever we start a binary search, we start at kind of the middle of the log, and we define the middle to be the greatest power of 2, which is less than the size of the log, to make it a little bit more stable. But in this case, for the log we have drawn out here, this is 16. And so we look in entry 16 and we get a binary ladder telling us, does the version of the label we care about exist yet or not? And in this particular case, we get back the answer, yes, it does. Okay, so we move to the left. And then in this case, halfway between 16 and the start of the log is version 8. And so we look in version 8 and we say, does the version we care about exist yet or not? And in this case, we get the answer no. Okay, so we move to the right. Then we get to 12. We get a binary letter again telling us, does the version exist? No, it doesn't. Then we get to 14, version 14. the key does exist, and then we go to 13. In version 13, it tells us that no, it doesn't exist. And so the conclusion that we can come to from this is, because we did this binary search, we know that version 14 is the first time that this label ever existed in the log, or this version of the label ever existed in the log. Or to maybe a weaker statement, which is that anyone else who comes and looks at the log will come to the conclusion that version 14 is the first time that this version of the label ever existed in the log. And that's kind of an equivalent statement, that anyone else who looks at it will come to the same conclusion, that this is where it should be. And so we know that that's the first one. We know that that's where, the owner of the label inserted it. And the fact that we checked that the label's value is the same at, version 16 of the log as it was at version 14, in essence, kind of proves that the value hasn't changed since the label's owner inserted it. Because we know the label owner checked that it was correct when they first inserted it in version 16, but it's possible that then they went offline and they haven't checked 16 yet. So we don't know that 16 is actually correct. We can't kind of take it for a given. We have to trace back to find where it was first inserted, because that's where we know that it was definitely checked for correctness. And then monitoring, if you kind of think about how monitoring works in this kind of system where search works in this way, well, that's, to be super clear, this diagram of the step we just walked through is an example of how to do search. And then monitoring, which happens afterwards, is basically checking as the log grows. We want to know that search paths don't change unexpectedly. And so in this case, the search path is not going to change because we started at 16. It's not going to change until there's a new power of 2, which is greater than 16, which is 32. So we can kind of sit around and wait until version 32 of the log exists. But when it does, we want to go in and we again want to get a binary ladder to check if the version we looked at before exists yet or not at 32. And we expect the answer to be yes.
So we have one person in the queue. Just Isha, is that a clarifying question?
So, quick clarifying question.
Yes.
Can you hear me okay?
Yes.
Yes.
Yeah, I was just wondering, so in the example that you were going over, Brendan, so why couldn't the version be changed in log 15, the number 15, and then changed back in 16 in that example?
Well, it could be changed in 15, but the point is that nobody would look at 15, because if you're doing this binary search, you're going to look at 16 and you're going to get the value there. And then you're going to look at 14 and you're going to get the value there. And you're going to check that they're equivalent. So if it's incorrect in 15, that kind of doesn't matter because no one is going to look at it. If the log was only, like if the log stopped at 15, then it's possible that someone would look at 15 and they would get that incorrect value, but then they would do the same binary search and that would take them back to 14 and they would see that the value stored in 14 is different from the value stored in 15. And they would reject the proof because they would see that there's an inconsistency. Does that make sense?
I see. Thanks.
Okay. Okay, so monitoring is checking that, as search paths, or as the log grows, search paths don't change unexpectedly. So once version 32 gets created, we want to go in and we want to get a binary ladder to check that the version we looked at before exists yet or not. And of course, we expect the answer to be yes, because if the answer is yes, then what happens is the search for whoever starts at 32 is going to move to node 16. And we already know after they look at node 16, they're going to move to 8. And then after they look at 8, they're going to move to 12 and then 14 and so on. So we know that they're going to sort of terminate their search at the same value we saw before. And we know they're going to get the same value that we saw before, which is what matters. And of course, if we look at 32 and then we see, oh, in 32, it says the version that we looked at before doesn't exist yet. What's going to happen is that people's search who start at 32, they're all going to move to the right. They're going to move into some unfamiliar portion of the log that we haven't looked at that maybe is different. And that is proof of misbehavior by the log operator because it's essentially trying to hide what it showed us before. That's how searching works. That's how monitoring works. To also kind of get into planned future work for changes that we want to make. The first kind of big one is replacing the prefix tree with some kind of self-balancing binary tree. And the motivation for that is because there's interest in using KT for non-privacy sensitive applications. And if you don't care about privacy, then using the VRF is kind of wasteful. So, getting rid of the VRF is like agreeable. The problem though is that the prefix tree that we use is a simple trie, and it's balanced probabilistically because everything that's inserted in it is the output of a VRF, and the output of a VRF is random and unpredictable. And so if you're inserting random unpredictable things into this tree, then you'd expect it to be balanced on average. But of course, if you're not using a VRF, you're using like a hash function or something, people can predict what the output of the hash function is going to be, and they can predict the search path they're going to create in the tree, and someone malicious could go in and try to insert a bunch of entries in the tree to make one specific person who they don't like have a really long search path, and then that person using KT is gonna, their proofs are all going to be really large and inefficient. It's going to be not fun for them. So the solution there is to replace the trie with what's called a left-leaning red-black tree or an LLRB tree, just because it's supposed to be fairly simple to implement and it's self-balancing sort of structurally, where we always know that the height is going to be proportional to the number of entries inserted versus a trie, which can be have very long search paths. Again, that's just because it's the simplest one that I know. But if you have strong thoughts on that, you're welcome to share them and we can talk about it. And then the other thing that we want to do is add explicit support for what's called proxy mode. So the current document and also the architecture document is kind of hand-wavy on how to do proxies, but this is actually a surprisingly common and also a really powerful pattern for deploying KT. So by proxy mode, I mean, like this picture down here, we have Alice who is talking to the transparency log. Alice doesn't ask about Bob. Alice actually looks up herself and she gets back a search response for her own public key. And she turns that into kind of like a credential that she can then send to Bob to authenticate herself. And the benefit of that is that it enables anonymous communication because of this, Bob doesn't have to ask the transparency log about Alice himself. He already has the credential from Alice. And of course, if Alice needs a credential back from Bob, Bob would go to the transparency log and look up his own information and get a credential and send that back to Alice. So that would prevent the transparency log from essentially learning who is talking to who. And of course, if the channel between Bob and Alice is anonymous, then that means that the transparency log can't really effectively control it. And so it gives you a really highly effective way to gossip about the transparency log and make sure that everyone is seeing the same values as everyone else. So yeah, this is, like I said, really powerful. It's also surprisingly common where a lot of applications I look at, this is kind of the right way to use KT. And so it's worth it to actually fully think through this and fully document it and maybe make some changes to optimize for this use case. And then some various smaller things. We've been thinking it would be helpful to have a stronger enforcement of time to catch some kind of attacks that could happen by the transparency log. So the transparency log right now can kind of try to warp time for different people and tell one person like, oh, the log is only, 1,000 entries. And then we tell someone else, actually, it's 2,000 entries. And we try to keep them kind of far apart in time. And of course, also, if you have stronger enforcement of time, that can improve the efficiency of searching and monitoring. Because if you know that, I looked something up and it went to a really old portion of the tree, then I know that anyone who owns data in that really old portion of the tree has already had the opportunity to make sure that all the search path is constructed correctly and the values are correct. So I can maybe omit some monitoring steps if I know that. Other things we want to do is switch the struct definition to COSI or CBOR because it's going to be more efficient. We also want to discuss recovery from user state loss and also recovery from log misbehavior. So if the log has like a glitch or something, we can recover it and not just have to throw the whole thing away. But yeah, that's all of the work that we have planned. This is all the slides that I have, and also I was hoping that we could discuss adoption at some point. But yeah, are there any questions or anything?
We don't really have a ton of time for questions. I want to make sure that we give time to Felix and Thibaut to present their presentations. So Prachi and I were wondering if we can go through the next two presentations and then have a combined Q&A at the end if there's time.
Yeah, that sounds good.
Thanks, Brendan.
All right. Next up, we have Felix. All right, Felix, you should have the control.
Yes, I do. I have the arrow here. Yeah. Okay. It's the first time I present remotely in this tool. I hope everything works well, but it looks quite easy. So, hey guys, my name is Felix. As you see here on the slide. To make things maybe a bit exciting, I'll do something out of character today. So for those who don't know me, I mostly work on protocol verification in the symbolic model. For example, recently we verified, I think this is a slightly out of date slide set. It's not the end of the world, but I think you had, no. Oh yeah.
We can try again.
Yeah, let's see. Oh, there is a revision. Okay, here you go. Let's see, Felix. I think this is the revised one. There you go.
Yes, great. Thank you. So recently, together with colleagues, I verified the iMessage PQ3 protocol in a tool that's called Tamron. It's a protocol verification tool, and currently I work on a new induction scheme for Tamron. So why do I tell you this? I tell you this because I want you to take away that Felix is a protocol verification guy. However, today my goal is to convince you that protocol verification tools are the wrong tools for the job to verify transparency systems. So, I mean, why do we care about all this at all? What we would like to do is we would like to prove the security of a transparency system. And security means we express its security guarantees in some sort of theorem. And by proof, I mean in a reduction to a set of assumptions. And ideally, our theorems and assumptions should be as clear as possible. Let's look at some related work, or how people did it in the past. I think Parakeet contains the best security analysis out of all the transparency papers I've seen. In the appendix, if I got everything correctly, it has 1 page of natural language proofs, but I must say, I don't understand the security definition. And of course, the security, this is a subjective thing, but I've tried reading this paper many times and sunk a lot of time into it. So I think maybe this problem scales to other people. I don't think it's the easiest security definition to grasp, and especially to connect to the actual systems. So I'm not saying this design is insecure. Probably Parakeet is secure, and I am certain that the authors have sunk countless hours into the security proofs. But I think understandability is a concern. And also the proofs here are not machine checked, and this is something I'd like to change. Later, other authors came up with a way to use ProVerif to, as they say, automatically verify transparency protocols in the symbolic model. This is pretty close to what I've done so far, but I think, and nicely, their proofs are machine checked, but I think that their techniques do not scale to our design, and I'll go into details on why I think that is on later. And then finally, there's a paper written by Andrew Miller, Michael Hicks, Jonathan Katz, and Elaine Shai. And they wrote this paper, Authenticated Data Structures Generically. I think it's a very cool paper. The TLDR version of it is that they design a domain-specific language that generates for you server and client code. And the type system of this domain-specific language gives you some guarantees. However, custom proof formats are not possible. This domain-specific language gives you also the proof format, how the hashes are ordered and all that. And I think their technique does not scale to all security properties that I think we should care about. However, this is another problem. I don't understand the exact guarantees that the type system gives you. I find the authors are a bit hand-wavy on how they link the security guarantees they give for their type system to the intuitive security guarantees I would expect from a transparency system. So let's look at some details. In the Pro-Verif approach, I already said this Pro-Verif is a protocol verification tool, and this all operates in the symbolic model. What does this mean? This means that cryptographic operations, for example, encryption or hashing, are reflected by functions that are uninterpreted. So you would define encryption, as you see there, just as a binary function, ENCR with 2 arguments. And then you give semantics to this encryption function by stating a decryption, an equation for a corresponding decryption function. This here is for asymmetric encryption, where you say if you decrypt something with the matching key as the argument, then you can unpack this to yield the message. These are also called destructables in Pro-Verif. The problem in the symbolic model is that you cannot model any relations on terms. For example, hashes. Variables in the symbolic model and functions are just uninterpreted. They don't have any value. So I cannot say that a hash X is lexicographically smaller than a hash Y, which is a problem for our design. For the same reason, you cannot, I put an asterisk there because cannot is maybe a bit too general, but I think you in general cannot model tree construction. So with these 2 constraints, you might wonder how did these people even write a paper? How did they manage to prove something about transparency systems? And there are 2 reasons. There are 2 ideas. There's one reason and one idea the authors employ. One reason is that they only consider blockchain-like systems, a CT, Merkle tree, and transparent decryption system. And these are all systems where the bit values of hashes don't actually matter. The only thing that is relevant is the transaction, the order of transaction, simplifying a bit. So concrete values are for the most part irrelevant. And then they in a very clever way, get around the tree construction problem by just saying that the adversary, the active network adversary that Pro-Verif automatically considers, is the person constructing or is the party constructing the proofs that the client consumes. This is a very cool idea, and I will borrow it a bit. So coming to the type system approach, how this works roughly is that values in this domain-specific language are either authenticated, so we assume that we can use them, we can authenticate them somehow out of band. For example, this would be the case for a root hash, or they are unauthenticated, which is basically everything besides the root hash. So all sorts of commitments you would like to store in the log. As someone using this domain-specific language, what you do is you write one implementation for all the algorithms that your system has, and then the compiler generates you server code, which additionally generates proof for unauthentic values, and client code, which additionally consumes proofs for unauthenticated values. And the proofs are basically stacks of hashes that match the function calls that you do, and then so the server puts it on, the client pops it off, da, 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 da. The cool thing here is that the security guarantees are for free, and again, there's a little asterisk here because they're not really free. You need to use their system, and that comes maybe with some real-world downsides. But I think it's still a very neat design. However, I'm quite convinced that the security guarantees do not consider any sort of time. So you cannot say, because I did query X yesterday or today, I know that query Y yesterday must return a specific value. And they also do not consider the interactions between different functions. For example, what an auditor would do and what a client would do. Okay, so the good out of both these approaches is in the Pro-Verif model, it's this idea of how the adversary constructed the proofs. I think this is a great insight. This matches the threat model, right? We don't want to consider any server code really, ideally. And this gives us an implicit universal quantifier over all the potential proofs that the clients can consume. And the type system approach shows that actually the algorithm details are what matter. And this also matches the discussions I've had with Brendan in the part. And that any sort of message exchange is really irrelevant, right? I don't really care the order of proofs, like what the server gives me in which order. As long as the things are correctly annotated and I can piece them together the right way on my system, all the important knowledge should be encoded in the root hash. And what the server gives me is just a clutch to verify that what they tell matches the root hash. So the idea that I have is that we should use a high-level language tailored to code verification. In this language, I think we should go for a reference implementation, and we should express all security properties of the transparency system on that reference implementation. Possible target languages I've been thinking about are Daphne, Viper, and Coq or Isabel. These are just examples. I haven't looked into the details here, but there are many options to choose from. The assumptions that I would like to make in the proof is that hash functions are a bijection, which is not realistic, but I think is reasonable for our efforts. At least it should allow us to get the job done. Ideally, we can reduce that any violation of our security properties yields a collision in the hash function, but I'm not sure whether we'll get there. This is to be investigated. So to make a concrete example, I hope you all like Haskell. If you don't, the slide might bring you sadness. But let's assume we have some CT-like transparency system, okay, where we can verify the inclusion of some keys with some number. No notion of latest keys, whatever. We just want to check that the key is in the log. So we have this verify inclusion function here. It has 4 arguments. I'm using my cursor. I guess you don't see my cursor. It has 4 arguments. A root hash that the user gets from somewhere else out of scope, a pseudonym that they would like to check the key for, then an int specifying, also a user input specifying the key version they're interested in, then some list of co-paths. That is the proof of inclusion. And then they either get some error out or they get a public key, or they get maybe a public key. They could also get no value if no such version exists. So a theorem I would like to prove, and excuse me, it's I made a small mistake. The L should be a I, and the L should not be all quantified. But basically, the idea is this theorem is a bit too strong because I need to handle errors a tad differently. But basically, the idea of the properties that I would like to prove on the code level or on the algorithm level are that for all proofs pi and pi dash, if we use a fixed root hash A and a fixed pseudonym P and a fixed key version I, then the result of the verify inclusion algorithms will always converge to the same thing. No matter what the server gives us, we will always come up with the same, come to the same conclusion as different clients implicitly. So yeah, what this says is that the server input is really irrelevant, just like in the Proverif approach. So what you just saw was a security theorem for one algorithm. I would like to generalize this in the future in 2 ways. Namely, I would like that security guarantees develop over time. Running an audit should give us provable guarantees of the past. If I audit now, I should be able to conclude that all clients that have made their queries on the respective root hashes should have seen the values that I saw. And I would like to connect different algorithms. For example, the presence of a trusted third-party auditor should allow us to provably reduce the loads of clients. The client algorithms should be able to become smaller while being able to maintain the same security guarantees. But if we remove the auditor, we should not be able to prove our security theorems. For the reasons of time, I will not go into the details here. In summary, what I would like to propose is to use a high-level verification-aware or verification-tailored programming language where we prove key transparency system secure considering how logs develop over time, and considering the interplay of different algorithms that are part of the transparency systems. Importantly, message exchange here is irrelevant. If we follow this thing, the bonus is that we have a reference implementation. So I would like to choose a generally intelligible programming language. This increases the constraints on the programming language to use, but I think it would be really neat, because then this has value outside the box. So this is new to Brendan. I think it really developed today only. But Corey reached out to me and said that he would really like to work on this. I thought I would work with it on it with a student here at ETH, but Corey said he is up for it as well. And I think that's great. So we will start with that soon. That's the end of my presentation. I guess we don't have any questions, so, or now at least. So let's hand over to Thibaut, right?
Yes, thank you, Felix. I don't see anybody in the queue or any questions in the chat yet.
If you have any input on this, please reach out to me by mail or Slack. You should find contact details on the internet.
All right, thank you, Felix. Okay, next up we have Thibaut.
Okay, and just to confirm, because like the meeting's supposed to be 1 hour, and you mentioned there would be like possibly Q&A at the end. Is the meeting sharp at 1 hour, or like what the potential for going over? Just to know if I should shorten my presentation to allow for Q&A for everyone.
Yeah, I think it'll
preferably.
be. Yeah, go ahead, Siobhan.
Oh, just that I was going to say, preferably, yeah, we'll be pretty sharp about cutting it off at 1 hour. But so it would be great if you can shorten it as much as possible. Yeah, and obviously, yeah, do whatever you think is makes sense.
Yes, I'll do that as much as possible, and feel free to ask questions at the end then. Okay, so everyone, hey everyone, I'm Thibaut. I'm working Cloudflare, and today I'm going to discuss witness ecosystem, which is kind of like some learnings we had with Cloudflare as part of like shipping an auditor for like when working with WhatsApp on key transparency. And hopefully I have control. No, I don't have control. Do I? How do I control this thing? Oh, now I have control. Thank you, Prashi. Perfect. So I will very quickly go over the evolution of KT deployments, because most people in the room, I think, know KT deployments. Then discuss out-of-band versus third-party for auditing. Then the difference between monitoring, auditing, and witnessing. And like this is kind of a new component that's being introduced here. Finally, a proposal to like have witness with guarantees and like finding questions, and hopefully we get to that point. Okay, so as we've seen in the various talks, I think specifically like on the first talk from Brendan and previous meetings, there's a lot of literature already on key transparency, and like this is due to like tireless work, I think, from a few people in this room, and these have come like slowly years after years. Some have been deployed like immediately, such as Connex. Some came a bit later and like benefited from like learnings from previous papers. And there are even papers which, to my knowledge, are not implemented yet, such as Optex or Electra. And what's of interest to us today is like the key transparency protocol, which is kind of like the latest installment of key transparency and its implementation. And that's what we will be discussing today. So first of all, reminder, before key transparency, what were the components for an end-to-end encrypted messaging app? You had a client and you had an application. When you had like a username, such as phone number, an email, etc., and you wanted its public key, you were reaching out to like the application server and like you were getting the public key. Now, first step for key transparency was you, instead of an application, you had an application which was a log, meaning like you had like a tree with which was representing the directory. And so on top of being able to say, okay, for like this username, phone number, email address, which public key do I have? Users were also able like to monitor to some extent like the changes, and third party were also able like to look at that. The thing is, there's like one attack that could happen with that, which is like a split view, in which case you could have like the log providing like different tree head to multiple clients, or log doing like some switch and permutation, which client might not be able to audit. And therefore, there was a need for monitoring / auditing to ensure that like every client was getting the same view of the tree. The current draft, like draft 01, is presenting two approaches. One approach is to have like out-of-band communication, which is left to discretion to the implementer, and so like clients would communicate between each other. This might present some like privacy risks, some availability risk, depending on the setups and etc. But this is definitely something which is possible to do and allowed and considered in the draft. Another option, which is the one we've deployed, like with WhatsApp, is to have like a third-party auditor. This means this is someone which is independent from the log, that is able to test for like what is like the current state of the log, or at least the current state it has seen. There might still be like some split view, but at least the auditor would guarantee that there's a consistent stream of updates that it has seen. The client could trust this auditor and therefore like follow the chain of updates and epochs that it has seen. There's actually like one subtlety compared to like what the draft is proposing. The draft's proposing for the auditor to both guarantee that like this is a consistent view, but also that every batch of updates, now that we have batch, is actually like valid compared to like the previous tree construction. And in our understanding, this was like in our deployment with WhatsApp, this could have been in some cases a bit like an added guarantee. Two guarantees you want is you want to know that like the stream of epoch is globally consistent, and you want to know that these epochs are actually like valid and valid updates to the tree. And so if we look a bit like further into third-party auditing, it includes both validating the global uniqueness and like the incremental behavior of these updates, and also like having some compute to like validate the state of updates, which we retrieve, at least in the case of WhatsApp, from a public bucket that the log is providing, guaranteeing that like we copy these updates so that they are available down the line. And this distinction between what is like a guarantee that like we've seen an incremental stream of epoch, and the second guarantee that like these epochs are valid, is very similar to what the certificate transparency ecosystem is moving with witness. And so now we'll introduce like a new type of like actor in the system. So like we have the action of monitoring with monitors. So in the case of key transparency, it's clients that like monitor their own key. Usually it's this is authenticated because you might not want everyone to be able to monitor everyone's keys, depending on your deployment. And it's tied to the protocol the log has. In a different fashion, you have like auditor, which in the key transparency draft are validating that the log structure is valid and the epochs are correctly constructed. It's usually done by a third party. It could be done by clients if they have like the necessary resources. And this should ideally be done on public data. Even if this is not the requirement, technically you could, like a certain log could have its data private, have third-party auditors come in and publish an audit that like they've run the audit and everything's fine. It can be costly depending on the protocol. It's less and less true with like newer protocols, but that's definitely something depending on like the frequency of the update, the availability, or like various construction that you might have, which like can be like more costly to operate. And finally, the construction that we want to introduce is a witness. So a witness is like a representation of a third-party guarantee. And the idea is like this guarantee can be timestamping, can be that all the epochs are incremental. It can actually be auditing the log. It can be that like I'm someone committing that like I've backed up the data, I have like some compliance, I provide a public API, whatsoever. And the idea is it works with multiple log protocol, which is important as well for supporting previous protocol that had been done, like previous logs that have been deployed throughout the years. And one log can serve multiple of these protocols, which allow to spread trust. This witness actor is being deployed at the moment, or at least envisioned to be deployed as part of the network. So if you want to onboard, like you're launching a new log, you can reach out to a public network, which would provide at least the basic timestamping feature for everyone. And if you need some like more specific about like your log protocol, that's something you can discuss with these witnesses. There's a first specification on C2SP, and definitely something we can like integrate and see how to discuss. I have one more slide with like the three third party that have existed at the moment and like the various consideration. Or this third party would guarantee that there's some split view resistance, which is like the first role that you want. Not all of them might provide like an HTTP API, which is something which we found important, or have different trade-off for surface use agility. One thing which is very interesting, I think, is there's a timestamp in both the witness provided for certificate transparency and the one provided by Cloudflare, which allow for like later auditing of the auditor to confirm that they've claimed like what they've done is actually like valid, which is very good for checking back. And I will stop here. There's more information on our blog, some documentations, and on the code base, but I will leave some time for questions, just generally for this presentation and the meeting afterwards.
All right,
Thanks,
thank you,
Thibaut.
Thibaut. Are there any questions? All right, I don't see any questions. Oh, we have Felix in the queue. Felix, go ahead.
Yeah, hi, Thibaut. Could you just repeat again what the witness exactly does if it's independent of the log protocol?
Yes. So basically what the witness does is it has like a certain message format, and would sign this message format saying it has performed some verification with a timestamp. So we imagine, for instance, in the case of the log protocol presented in the draft, it would sign like the timestamp and along with like a hash of like the tree head, and possibly like the hash of the tree head. And associated to like that signature, it would guarantee that before issuing a signature, it has audited the update, or before issuing that signature, it has like backed up the data from the log, or before that signature, it has guaranteed that like all the epochs are incremental.
Okay, yeah, that is what I have thought initially, but how is that then independent of the protocol?
So this is independent on the protocol because this signature format does not tie exactly to what you've done, like to the message format that you've done. Like the witness format is just like a timestamp and a signature, like over a certain message.
The message format is protocol independent, not what the witness does.
Yes.
Okay, great. Thank you.
And then depending on which witness you are, you could like guarantee that you would do something before providing this signature.
Mm-hmm.
And to add to Brendan's comments, which is like the separation between verifying the global view and verifying the structure of the tree. This is something that came up with WhatsApp because one of the things they wanted to do, and Kevin is in the room, so feel free to add if you have more comment on that, is that they wanted to ensure that like the global unique view could be delivered very fast. And this is like a very quick check to perform, while actually auditing the transition between every epoch is more costly and required more resources. And so they didn't want to delay all the update that they had pending that verification. So like the uniqueness is done synchronously, while like the actual verification of the structure is done asynchronously.
All right, great. We don't have anybody else in the queue, nothing in the chat. So I think we are good for now. Oh, thank you so much. All right, that brings us to the end, and we are very close to the time. So as next steps, if anybody has any more questions, clarifications, you can use the Slack channel or just post on the mailing list. I believe we'll talk adoption as next step, but we'll continue that conversation on the mailing list. We don't have enough time to go through it today. With that, Siobhan, you have anything else?
Yeah, I think just to add to that, the plan is to adopt a protocol draft and document. So I think we are looking for feedback on that on the list. So if folks have opinions and thoughts and questions or anything like that, I think proactively like sending that to the mailing list would be super helpful for both the authors and us as the chairs to figure out next steps. But yeah, thanks all for coming out, and see you next time.
All right. Thank you.